Our next lecturer is Miodrag Milanovic with the topic FPGA for software developers.
Thank you, and thanks for coming here. Well, let me first introduce myself. Well, as you said, I'm Miodrag Milanovic. I'm a software developer here from Novi Sad, Serbia. I work in Livanine company, and I'm a software developer since year 2000. So I had mostly experience in languages like C, C++, and afterwards on Java, C#, and everything else what happened. Yeah. And during this time, I also worked on I also work on some open source projects. Maybe you heard of MAME. That's the arcade emulator. And also it emulates the computers and stuff. So basically I was leading that project for about 5 years. And during that time I also learned a lot about computer architecture, but also I was very interested in how everything works. And since I finished as an electronic engineer, basically I give myself a freedom to try to investigate a bit more. And one of the things that I would like to share with you is how to do FPGA development as a software developer, basically. And as I said, here on a U-boat, and I will tell you why. Well, this talk have a B-rated movie scenario, so basically it's something like Sharknado or something like that, but not that good, yeah. So we are reverse engineers from present time, and they sent us back to this U-boat 1206 during the World War II, and what we have to do is to find an Enigma machine and create a copy of our own. And only thing that they gave us is this little FPGA board and this laptop. So basically we have to take care of everything ourselves. And we don't know how Enigma works, and we don't even know how FPGA works. So we need to learn all of those things, and we have 1 hour to do that. Well, also for the fun sake, we are going to make a little diversion at the end, and if you take a look at Wikipedia for this U-boat, you will find what we actually did, because we already did that because of the time travel and everything. So you can check that later. And because you're all, most of you here are software developers, but anyway, we need to do some introduction. For those that are not, and that maybe are willing to learn something about this, just to be able to follow up. And first we need to remember the Boolean logic. And as you know, it's a math thing from more time ago than there was computers and everything, but we still use that. And here we can see just the truth tables for the some Boolean logic circuits, and just you see if we have for example and only epsilon is only 1 in cases we both A and B are 1. For the NAND is just a negative 1, so you have 0 only in cases when both inputs are 1. And for the OR, it's as still as there is 1, at least input that is on 1, we will have 1 as an output, otherwise we have a 0, and so on. And the next thing that we also need to be aware is our flip-flops. Basic flip-flops are just simple memory elements. They hold 1 bit of information. And we need to know how they function, because we need it as a building block in our architectures. And as we see here, the most used one is a D flip-flop, and that one have on one input, and also second input is a clock. So basically, we only change our outputs depending on input on the clock change. So as you can see here on the D part, you can see that the D is changing, but we are not changing our output unless there is a clock signal. So we can also prevent some jittering on the input signal. So now the question: what is FPGA? FPGA is field programmable gate array. So that's the abbreviation for it. And what it consists of, it consists of the so-called LUTs, and those are the lookup tables. And basically, you are doing multiple Boolean operations there, and you produce from the, in this case, there is a three input LUT, you produce one output, which is epsilon. And also you have a D flip-flop in that element, which you can, you have a clock for it, and you can use output of the three input LUT, or you can use a separate input for it, depending on the needs. And that's the basic building block of all FPGAs. So basically you are using that one element multiplied thousands of times just to get a programmable device. And you may say, okay, but why we use such a complicated device right now? Well, thing is that in the past, and during the 80s and end of 70s and beginning of 80s, we had that large progress on in computer industry. So basically, what was needed is during that time, I mean, many of you probably, some of you at least remember that time. And during that time, there were a lot of companies which basically produced various types of computers. But what was interesting is that most of those companies were actually producing the elements for the components, I mean electronic components. So for example, big companies had their own production of the chips, and so they reuse it and to make the computers basically, and all the hardware which is of the similar usage. And the problem there was that they need a lot of elements basically to build up some simple things like address decoders. And for example, it's quite easy. You can use a ROM in that case and use it basically to get the same combinational logic just using the ROM. Or you can use afterward, they introduce PLA, which is programmable logic array, and then you have GALs, PALs, and basically all of those just make you use the combinational logic so you can produce something. And as a top-end production, they had CPLDs, which just have a large number of those. And what they were all missing were flip-flops. Basically, they just did combinational logic. They couldn't do any sequential logic. So you would need to do that sequential logic outside. And that was the really problematic part. And that is why we had an FPGA. Also, the part of the FPGA is a clock tree. Clock tree is one important thing because you need that clock signal to be deployed to the all D flip-flops inside your FPGA. And in most designs, you're basically doing everything or most of the things under one or at least few clocks. You don't do multi-clock designs basically, because when you do that, you have a problem if you don't do it the right way. So basically, there are tricks which can save you from that. But what the clock tree is that you have one dedicated pin which gives you the clock signal, and that clock signal is then basically like a tree propagated to the all elements like this. Also, we have I/O blocks. I/O blocks are just connected directly to the pins of the FPGA output pins, and basically you can then define if that pin is input or can be treated as an input or output, and you can also put it on the high impedance, for example, if it's output, and then you can manage the buses and so on. Some of the FPGAs, most of this nowadays are having the dedicated RAM because in some designs you basically have the need to have a RAM section, and you don't need that much combinational logic. You just need D flip-flops, a lot of D flip-flops, and address buses and so on, and you have that implemented inside. So your tools can then recognize that and use that part instead of these flip-flops. And producers of FPGAs are Xilinx as the first one, and then because they started basically producing this, we have a large one like it's Altera or Intel nowadays because Intel acquired Altera, and we have Lattice, Microsemi, which are small producers. And well, we now need to know where the FPGA is used. Well, it's mostly used in prototyping. So basically, when you're starting some new project, you would spend a lot of time if you're doing those things with the discrete components or off-the-shelf components. So it's much easier that you use a chip, off-the-shelf chip, program it, and give it a functionality that you are needed for this project. Yeah, also it's used on the small series commercial products. For example, oscilloscopes mostly have those inside, and you have then possibility to change basically even the functionality of the whole device if you arrange it well at the beginning. Also, because FPGAs have a low power consumption, you can use it basically in anything then you need it, and you do not have enough money for the ASIC to produce. Well, you can use it for implementing security algorithms. I mean, we are going to do that in a simple form, but you can do it on a much bigger scale. And for example, you can do it for network packet analysis. And one of the examples would be the Microsoft platform called Catapult, which they're using in the data centers. So you need a way to make sure that only machines that are on your network basically see each other. And you have in the cloud, you have a large number of machines, even in virtual machines in one server, that basically need to communicate between themselves. And how do you do that when you need to get, things like 100 gigabits per second? You can't do that by using some CPU because you don't have enough time. Basically, you need to put FPGA, take directly the network data, do the analysis, see if this is for your part, and then just propagate that to your NIC, basically. And we have, of course, many other more usable places. So what's the process of development? That's the thing that we need to know before we start. Well, we have the analysis. Analysis is the part of when we do the actual parsing of the input language. Input language, first that was used was VHDL, and VHDL was sponsored by Department of Defense of United States. So that's the reason why it's robust, well-defined, but it's also quite old, and it's based on ADA language. And I don't know how many of you here program in ADA, but it's not that easy to understand, and if you are a software developer in any other language, you will have a problem looking into that code. And then we have a Verilog, which have a C-like syntax, so it's much easier for us. Then we have a process called synthesis. Synthesis is when we transfer that HDL, high definition language, basically, or schematic, to the netlist. And what netlist is basically a thing that we afterwards use on place and route. So we know that we have those LUTs on the board, and when we need to create a final product, basically place and route tools takes our so-called compiled code and do the place and route for that specific FPGA technology. And we have some part that usually is skipped in documents, but it's almost always part of the place and route. And that's basically creating a bit stream out of that data. And the bit stream is what we actually program on the device. And we also do have the timing analysis as a part of development process. And the timing analysis is really important because then you can see if that product is ready to run on these speeds that you have provided data for. And we have simulation because we need to trust our design. In this case, we are going to use the open source tools. We have Yosys, that is the Verilog synthesis tool by Clifford Wolf. And the good thing is that I didn't mention that before, but thing is that all vendors have their own tools, which are you have a free version for the simple FPGAs, but if you wish to use something on more complex, you need to pay $10,000 approximately per year just to use the tools. And that's probably not everything, because you will probably need to use some of their IP, intellectual property parts, and those you need to pay as well, and then you just have you pay, and then it's just not for prototyping anymore. And with this kind of tools, basically, guys are trying to make the open hardware available for everyone. There is also Arachne PNR. That part is doing the place and route in this case. And we have the project iStorm, which is basically assembler part, which will create a bit stream for us and have a programmer as well. And this is only right now for the Lattice IC40 FPGA. And reason for it is because it's basically what the guys did is they reverse engineered whole code, how this specific FPGA is organized, what number of parts it have, and basically they made the tools to support this. What we also support right now is that Yosys can generate code that is ready to be used by the commercial place and route tools. So you can use this in combination with Xilinx tools, but you can't skip all the steps. And we will use the Icarus Verilog by Stephen Williams, and that's for the simulation. And Verilator, which we will use to be able to create C++ tests. So it's easier than for us to do the testing of our design. In this case, I use this Go board by Russell Merrick. It's a simple board. You see it's very small. It has just that one FPGA with 1K of elements. And if you can see, it has some additional hardware here because it's supposed to be used as a learning platform. And on his side, you can find a lot of nice tutorials for the beginners. Well, now we come to the point of Enigma machine. Well, you probably see these images before, but let's see how Enigma really works. Well, it have those wheels, basically, which are initially, those wheels have a different types with a different letters basically on positions that are we define here when you press the button on the keyboard, it basically goes first through the plug board, which is basically just wires connected in original case, and then you have this static wheel which just propagates the signal, and then you are basically going through their wires that are going through the wheels to the next wheel. And you just need to be aware that Enigma is electromechanical device. It's not electronic device. So this is maybe not the best thing to show for the FPGA, but anyway, we can recreate it in our case. So we have the signal, blue signal, you have this red signal, sorry, going through, and you see that it's going through all the wheels. Then there is a reflector, which is basically doing the same thing, but it's just information is going back to the first wheel. And then we have the propagation back to the beginning, and then you have the light going on. And there is a link down there. It's a JavaScript implementation, online JavaScript implementation of this Enigma machine, which in this case we use as a reference, basically to get a knowledge how it really works. This is the original scan of the original, of course, Enigma settings. These Enigma settings were placed by the date, and in the first field there is a date for that month, and you have which is the order of the wheels, and you have the start position for the wheel for that day, and then you have the plug board connections. At the end, you have the proposed starting codes, so basically which you are going to use during the day. And that's about it. You know, this is what you have for each day, and both sides have these on their in their books. So this was predefined. But these last column, basically what they did, they usually send those three letters first, and then the real message start when they start to changing the. Well, we now need to do some planning, and if you ever did real software development, you know that weeks of programming can save you hours of planning. So basically, sometimes you really need to think ahead, at least a bit. I mean, you always do that, but you're sometimes just not aware that you're doing the planning. You're thinking in your head, you're examining things, you actually are planning. So we will have this architecture like this. So let me just point out. So we have this UART in. So we will use the USB connection, and we will basically have USB to serial in our case, and we will get the signal over the terminal, which will go to our UART RX, so receiver. And that received information we are going to deploy to the Enigma state machine. That's for now. And we will get that output over the UART transmitter out over the USB back to the terminal. We will also use that output over the two. We have on this board, if you can see, we have a 7-segment display, two 7-segment displays. This is enough for us to write an ASCII code, basically, of output information. We need to do that because we need some time to debug, to see if we are really getting that information. Maybe we have a problem in transmission, but we need to see if that is going out or not. And we will display that here. And also we will have one clock, which is 25 megahertz in our case, and that we will deliver to everything. And we will use some LEDs for debugging. And that's about it. This encoder section is what we actually see on the previous one of the previous images. So we have we will have the ASCII code, which is coming in. We are going to the plug board, rotor 3, 2, 1, reflector, 1, 2, 3, plug board, and we have output. So that's the way how the real stuff works, and we will just do that. No changes there. And we will have, because those rotors are actually rotating when you press the key, basically rotors are going around and first change, and then you are getting the current going through that. So we need actually to emulate that. And we have a simple state machine. Well, you know what are the finite state machines. So we have basically 4 states in our case. We have the one in which we will do the reset and rotate. So we will basically prepare for the first. We will set up the initial state and do the initial rotate just to save a few steps. Basically, we could do that later, but then we will have a 1 or even 2 additional steps in our state machine, and it will become slower. Please note that each of these steps is just 1 clock of 25 megahertz in our case. So you are going to idle, and then you're waiting basically for UART connection to come in. So when you are notified that there is something, you check what key was pressed, and depending on what key was pressed, we are going to encode and rotate for the next, just to prepare. Or if we press escape, for example, we are going to reset everything just to come to beginning. And otherwise, if it's something unknown, please note that Enigma machine just have from A to Z, nothing else. It's a simple 26 key keyboard, no numbers, no special characters, no anything. And at the end, we have this encode and rotate, and we are going back. So we need to take a look at the Verilog. So this is how the simple parts looks in the Verilog. And as you may see, each of these starts with module. Module is a keyword which basically defines one of the building blocks we have. And you remember that at the beginning we said, okay, we will need something to decode ASCII code that comes. And we will need something to encode. This is the decode is at the end. Basically, encode is at the beginning. So we are basically getting the, you can see the difference between the first definition and the second one. So second one is the old style C declaration. Basically, you can see the variables are defined afterwards. So you just name them and then define them. And here, but you can also put them all in one line. So it's just for those that are used to that. And you also have types. So you define something as an input or output for your model. But in this case, there is no keyword var. But that one is default one. If you don't put anything for the input or output, it's basically a var. And you just put the width of it. So this is 8-bit ASCII. So we are getting the 8-bit ASCII, and we are getting the 5-bit output as a code. And we are also getting 1 bit as a valid signal. This is ternary operator basically here at the end, you can see. And that's what I like to do when I like to confuse those that are doing the code review. Then you put everything in one line, and then nobody knows how it's working. But in this case, it's just easier because you need to do assignment in one line. You can't do it in the few lines because each output, basically, you declare how it's calculated. You can do it in multiple lines, but I will show it how it's done later. So what it does, it checks if this is the ASCII character for the big letters, or it is for the lowercase letters, and if this is out of that range, then we place a 0, so it's not valid, and if it's that range, then it's 1. So we know that our next thing that we define is valid. Code is actually ASCII. It's if it's over if it's in lower sections. So basically, it's higher than 5A, then we use this one, this calculation, and if it's lowercase, then we use this calculation. So we get it from 0 to 25, basically. I mean, it can be out of that range, if you can see here, because if we press something else, but we will have this valid flag, so it will tell us, so we don't care, actually. And what is important here is that these lines are actually performed in same time. So that's what you need to think. I mean, it's a different logic completely when you're doing the software development. Then the order makes sense. But here, you don't need to take care about the order. Basically, I mean, if you look things in order, then you're doing a bad thing, basically, because everything is done in parallel. That's the whole point. We here have, I explained these inputs and outputs, and basically this is just combinational logic. So we don't have any registers, anything. Let's go to something more complex. This is a reflector encoder. Basically what we have is we have these B and C reflectors, so we can use any of those. In our configuration, we send reflector type as input. So basically, depending on that, we will use one of those outputs. So basically, for there. And if you take a look here, you will see that there is now always at star. That means that it changes on each signal, any signal change for this module. So if we have any input signal that we have here defined, if anything changes, this will change. So it's a combinational logic still. I mean, we didn't put any clock inside. And this is how you basically doing. You're having if something is equal to 0, then we do this block, otherwise we do this block, and you can then have a case, basically. And case, if you need more lines, you need to put begin end, otherwise it will treat it just as a next case. So this is how we do it. I mean, this is purely for educational purposes. This is not how you should create this part, but just to be shown. Oh, sorry. Now we have this sequential logic and instantiation. So basically, this is a bit of a tricky one. It's a rotor, and we need to. That was the bottom part. When we introduce a signal, we need to rotate first all the 3 rotors. And as you may see, we have the output registers. So we have reg. That means that it's basically D flip-flops are used, and we keep our state. Also, you have the variables, like you have in C. You will have vars. So var is a variable, which you just keep it temporarily, and the register is something that you wish to keep for the next run. So you can put initial state for it, so that is how it will be initialized. And here is instantiation. Instantiation is basically you put the name of the component of the module, basically, in which you have defined. You put the name, how will call that instance, and then you propagate parameters by name. Dot name of the component, and then in the brackets you put the name of your variable that is mentioned here. And here we have a clock. So we need to have a sequential logic. The rule is always keep just one. So if you're using a clock, then you should just react on the clock, nothing else. Everything else can be checked inside that clock cycle. So you have here a reset, and we will reset only on a positive edge, basically on each clock. So we will not have situations then when the reset is changing, for example, fluctuating, that we keep resetting device, and then we will not be able to follow up. And here is just the logic, how do we reset, and you can see that here we have sign less equal, which means assignment, basically. And those lines are assigned in the same time. Order is not important, you know. And in the always blocks, you can put, if you put equal, then the order matters, you know. It matters. And if you put less than equal, then it's assignment. So it doesn't matter. I mean, I just want to initialize this all at once, you know. And here you can do the checks. Please note that you are actually checking, you are taking the current. So if you do set something here, you're still here in the next line have the old version of the value. So you need to think everything is in parallel. And we need to test this somehow. And this is why we have test benches. Test benches are just modules which don't have inputs nor outputs. They have here variables defined. I just defined a bunch of registers, set them to 0, you know, initialize this rotor control. And what I did, I said, okay, always on each 5 time, it's a nanosecond by default, but you can put the other unit basically if you define it at the beginning of the document, and we will just clock basically. We will change the clock to the negative of the previous one. So we will just clock. And here initially we just have the initial block which will do the we will dump everything in VCD file. We will dump vars from this instance, basically. And then I said, OK, after 5 time units, reset 1. After 10 time units, reset to 0. And then I have a for loop. For for loop, you need to have a finite number. So you can't use register or var as a value here. You can just use some finite number because you can't deploy that then on device, or I mean in this case it's simulating, but anyway it's not by the Verilog syntax. And we have here then okay, put the rotate on 1, put rotate on 0 after 10 units, and then display what we have. And what we actually get out of that is this output. So we have how the rotors are actually moving. You know, you can see the values are changing, and because there is also a knock point on each rotor, so basically when it reaches some position, it then moves next rotor around. And that position is basically also different per rotor type. So that's just to make this more complex, basically. And here we have a GTK view, which enables you to see that VCD file. So you can see the clock here. You can see the values of the position. And you can see the rotor, how the rotor is running. So it's going from 0 to 21. And then it goes 1. It rotates. Also the second one, because it's a point here. And we have going to 22. So these are the codes for the lateral. And we have that knock point here, you know, so it's exactly in the same time when this occurs. So we know that now we have basically implemented this well. Oh, sorry, this goes. Here is the state machine. So basically everything we do in the state machines because we need somehow to make that movement between the reaction on event and waiting, because there is no sequential things. You know, everything is going in parallel. So you need just always to check. You always need to check. Otherwise, you can't say, okay, wait for 5 seconds. That doesn't exist in a Verilog. You know. So you do the state machine, and then you can, you know, just depending on the value, you just change the state, set some values, and then check some variable, which is input in this case, and see to change state depending on that. So if it's valid, we go to encode. If it's not valid, we go back to the idle and then check again and so on. So encode, and when it's done, we basically go back to idle, and that's how it works. So we have this Verilator, which is basically enables us to use the C++ to test our code. And how we are doing that? Well, basically, it's compiling the Verilog and created C++ classes, and then you get the same model basically implemented inside C++ class. And you do the thing like here. So you set the clock, and you say evaluate. Set the clock to again. I mean, we are just storing which one, so it's basically changing the states. And then we have this part here, which enables us to just to get it enough clocks to evaluate, and then to see the output and to check what the output is. Sorry, this is, yeah. And how do we run it? Well, we have this large command line. We make output, and we get this. So we have, I'm just sending A, letter A, and then I get these codes. So this is first press of A, I get B. Next press, I get D, then Z, G, O, W, and so on. And what is important for the real product, depending on, I mean, you have, for each of the chips, you basically have some output pins. And those locations have just numbers. There is no purpose, because you can connect anything to any pin, basically except the clock, which is basically always connected on the specific pin for the clock table, clock tree, sorry. And now we just here, we have this constraint file that basically defines just the names for each of our ports, what is the location. And we are compiling now everything for the Go board. And these are the steps. So we just prepare, compile everything, we do the place and route, we pack everything, do the timing check just to see how fast we are, and do the programming. And when we run example, we run it something like this. We can use PuTTY or anything else. So it's a terminal. We type message, and what we type here really was welcome to Balkan. And so we try this and set to same, and just to check, okay, we entered same keys that we got encrypted, and we see that it's we got the same text basically back. What is important for the Enigma is that when you set initial settings correctly, and then you type a text, when you reset back to the same position and type that encoded text, you will get the original back. So we can test both sides basically with our. So let's do some live demo. I will put it like this. Okay. Okay. We have. I will connect the board. So we have board is currently running this code. We can. There is a flash, 1 megabit flash on it. So basically, FPGA is always empty. There is basically nothing, never. And when you start it up, you basically need to provide a way to put that bit stream inside. And it's automatically here done by using this this EEPROM from one flash size of 1 megabit. And we can here see the, I will just need to zoom it in a bit. So, okay, let's do the make clean. So let's prepare everything, do the make. So we are basically generating the output here. It takes some time for the synthesis. This is not that bad. It can happen that some large things are taking almost a day full day just to compile. So it's a really slow process. So basically what you did is you do the module by module and test module by module, and you split everything as you can. I will now, because it's here we have it, and I will do the make prog. So I will program it. Okay, it's out of date. You know that. Okay, and now we are having the this code again. I can put it here just to make it prog. So you see that it's going off, and then it's programmed and it's resetted here. So the new program is start running. I will open the serial port. It's in this case it's serial port 4, and we are going 11500. Okay. Sorry, I just need to put this down and to zoom it up. Oh, sorry. Not sure if it's doable here, but okay, I can press. I'm not sure if it's seen, but let me try to change setting. It's really small. Nah, not sure here it's possible. Probably it is. It's just too small. But here, anyway, you can see that we have the ASCII code for the output. Yeah. Okay. Yeah. You can see a B letter, and then the next letter. Now it's D, Z, G. I'm pressing just A button, nothing else. So I'm just pressing A. You know. And I can just put it like this. So if I go escape, I just put the enter, and now it's resetted, and I just do press A again. So it's again entering. So basically I'm resetting to the original position and then resetting everything back. So this is how it works. I just put it off. Okay, and. One thing I think I missed here, because it changed the quite fast, is that we skipped this one, these two slides here. Oh, sorry, it goes. I will just loop through. There are a few details more that are important, and there is also a way to define the memory. So basically, what we can do is for the rotors, because there are a lot of combinations basically here, and what we can see it's basically a ROM. I mean, there is nothing else. So you just address a position and take a value how it's encoded. So basically what I did here is I implemented a ROM, and then we have a sequential logic to take it out of the ROM. And here is what's the content of the file. So basically you have letter E, letter K, letter M, and these are the codes for it. And there is in the project you can see basically the Python script which will enable you to do this. And also, this is also the one that skipped. It's for the hex to 7 segment, and you have the how it's basically you can use the registers. So we can now go back, and here you can find the full source on the GitHub. And also you can find more information about this Go board at the NAND channel, and also there is if you wish to order it, you can just sign it for Enigma code, and you will get a 10% off. It's till the end of September, so basically it's for the people who are here, and those that will watch will basically skip it probably. And there is also FPGA for Students site, which have some large number of nice tutorials. So you can also use that as a reference and to try out some new work for the FPGA. So if you have something to ask me, please do, and that will be it from my side. And yeah, I would just like to show you a few boards. So we have some additional. So this one have an 8K element, for example, and it's called Black Ice. It's also open hardware, and you can use same tools like here. And you also have this one doesn't have anything additionally, but you can use the PMods basically to edit. And what people are using FPGAs as well are recreating old computers. So here we have a ZX Uno, which is basically a FPGA version of the ZX Spectrum, but it also can emulate a Commodore. It also can emulate even a PC XT. And you have a joystick ports here. You have a VGA. You have a SD card when you store the files. So basically, you just have one large FPGA here, and you have a flash, an SRAM, and that's basically it. I mean, you just have a few ICs design, and you can put the whole computers from a large number of computers for 80s. You can put here basically and run them out. So yeah, that would be it. Sorry. Thank you. If someone have a question, please. Yeah.
Yeah, hello. I'm interested for the open source tools. What is the support for the IP modules? Do they have something similar to Xilinx modules, which can be?
Well, basically, the whole point of the open source is that you don't have the IPs. Basically, you can use some open hardware. Define the. I mean, there are modules that are public, and there are collections of them, and there are few projects that are basically doing that. And you can also, for example, find RISC-V implementation, which is completely free and written in Verilog. And it's also done by the same person that did the OSIS, so it's Clifford. And the good thing is that you can, you just download it, put it in your design, and use that module as a part of your design and create some RISC-V machine, basically. So there are projects. There are also projects to make that building process easier. To download those modules for you, something like npm, but also but it's still it's just starting to grow, and we are now in position like the software industry was in the beginning of 80s. So basically everything is paid in the hardware world, and that's kind of a problem because you need some. Someone from open source world to compete with in order to get better products, because Xilinx will not do the bug fixes if there is no critical guy there waiting for that. They will just let it stay, but if it takes too much time for them. But basically the good thing with the open source is that they're pushing much harder now, and they're taking taking the ticks off, and then it will be, I think, much easier for the future when more tools are coming open. And
okay, just one more question. What is the position for the closing your source? Is that an option? Can you encrypt the files, or it has to be open source?
No, you don't have that limit. I mean, those are the compile tools, basically. I mean, your solution when you're making the FPGA, you can make it closed source. It's not a problem. You're just using. It's like with GCC. GCC is open, but you can make a commercial product, which, I mean, it's a tool for building. Basically, it's more like if you're using modules which are GPL, for example. But most of the modules nowadays are MIT or licenses that enables you to use it in commercial as well. Okay, so you don't have that problem. Yeah.
Hi, I have a question about the FPGA support. You said that currently only this lattice IC40 is supported, am I right? Yeah. And these three development boards that you have shown all use the same FPGA?
No. These two use the lattice.
Okay.
This is with 1K elements. And this one have 8K elements in an ARM chip, ARM Cortex M4, I think, on it, and so you can create a larger basically products on it because you have more space, and you have also more RAM on it and PLLs. It also runs on 100 megahertz, and this one is on 25. And this one is with Spartan 6. It's from Xilinx.
Okay.
Yeah. These are the smallest ones, so I bring those because they're, But the thing is that prices for playing is, about $50 to $100. Then you have something mid-range. It's $200 till $500, but the professional tools are, $3,000 and more. It's really expensive sport, basically.
Okay, thanks.
Thank you.
More questions?
Yep. Okay. That's it. Thank you. Thank you very much for coming.